Okay, 6 o'clock. Good evening, good afternoon, wherever you are. Um, and welcome to the Southeastern Michigan IEEE EMC Society technical meeting. This is January the 15th, 2026. And again, welcome everybody and thank you for joining us today. Last I checked, we had 45 registrants, and we'll see how that goes as the meeting progresses. My name is Scott Lytle, and I'm the chapter chairperson here in Southeastern Michigan. Um, right after this meeting concludes, stick around, please, because we're going to have a drawing for 3 Amazon gift cards. We're going to have a 100, a 50, and $25 gift card. We use a random number generator against the roster, and that's how we do it. And you must be present to win. So if we call your name and number and you're not here, we move on to the next person. Um, Next month, our speaker is going to be Keith Frazier, and I'm still putting that announcement together. So be watching your email for that. There'll be the third Thursday in February. Tonight's meeting is entitled Basic Parameters of the Site Standing Voltage Wave Ratio for Open Area Test Sites, or OATS, and Semi-Anechoic Chambers, or SACs. And this is going to be based on the CISPR 16-1-4. Speaker tonight's Lou Feudi. Lou has been product safety, EMC, telecom, and Belcore engineer, engineering manager, salesperson, sales manager, and corporate trainer. He has worked at Underwriters Laboratories, Intertech, TUV Rhineland, and U.S. Technologies. Lou has also been a global and U.S. sales channel manager selling equipment for Thermo Fisher Scientific and Keytech, Tesec, Amatec. He has a total of 44 years of experience in the compliance testing industry and has authored a number of articles for Compliance Engineering Magazine and In Compliance. Lou is currently U.S. Sales Channel Manager for Raymond EMC, the Anechoic and Semi-Anechoic Chamber, Reverb Chamber, and Shielded Enclosure Manufacturer. Louis, you got to unmute, Louis.
Yes, sir.
Okay.
Well, everyone, good evening. Thank you again for the invitation to speak tonight. I always enjoy doing so. And at the same time, I always enjoy meeting with you guys. Hopefully, maybe next year I'll be able to come up in person. However, this year we thought we would go through the SVSWR, as we refer to it very often. It's the semi-anechoic, or excuse me, the site standing wave voltage ratio, or voltage wave ratio, which is used to qualify chambers from the 1 to 18 gigahertz range for 3-meter, 5-meter, and 10-meter EMC chambers, in accordance with CISPR 16-1-4. Next, Scott. What we'll be going over is some of the basics. I've done presentations for you guys before that went over NSA testing, which is normalized site attenuation for the chambers, and that's usually from the frequency range of 30 megahertz to 1 gigahertz. It's a separate application. However, some of the stuff that we're going to go over today is going to be a brief review of what I've talked about in the past, and then we'll actually get into qualification of the OATS or the SAC or the FAR for SVSWR. Scott, if you could, please. So a compliance test site is basically an open area test site. An open area test site, as defined by CISPR 16-1-4, is ideally a infinite ground plane with no reflection, no no items, no materials, no obstructions, nothing that could cause a reflection or any other way of modifying or changing what you're trying to read as a or measure on the site itself. That is basically the idea of the ideal aspect of open area test sites. However, In addition to that, there is no ambient noise whatsoever in the area, allowing you to be able to take measurements directly off of the chamber or off the product. However, in today's busy world with Wi-Fi available almost everywhere nowadays and broadcast quite often, and radio signals, TV signals, and everything else that's basically broadcast, it's difficult to find an open area test site location that's going to be quiet enough where there's no ambient noise. So a lot of customers defer or move over to open air to semi-anechoic chambers and fully anechoic chambers. Um, as a result, there are requirements that are necessary in order to qualify those chambers, just as they are for the OATS site. The qualifications are the same, so you can. This testing that we're going to talk about is going to be consistent with both SACs, FARs, and open area test sites. But at the same time, it is necessary if you have any kind of enclosure around the product, you are required to do both NSA at multiple at multiple locations on the turntable, which would be usually center, left, right, forward, and you also have to do that with SVSWR. Next, Scott, please. So some of the things that you're concerned about with regard to an open area test site is that you have a quiet zone or an EUT volume that is theoretically, again, an ideal open area test site. It's perfectly flat, perfectly conducting ground plane, infinite area, no reflecting objects on the ground plane itself. The volume or the quiet zone is the quiet area. It's the cylindrical area above usually the turntable, which encompasses the EUT completely. And it is that area that has to be qualified and certified. And we do that by doing NSA and SVSWR testing. Next, please. As I jumped ahead, the EUT boundary area or the EUT volume encompasses the product, the cable racks, and 1.6 meters of cable length. And again, for measurements from 30 megahertz to 1 gigahertz, that's for NSA. This is going to be SVSWR. So we'll be talking about measurements from 1 gigahertz to 18 gigahertz. Next, please. As I mentioned earlier, quiet, level terrain, ground plane, free of obstructions, no trees, no buildings, no electrical lines, no fences. Optional weather protection is there. If you do use optional weather protection, then you do have to, once again, create that or qualify the quiet zone. The quiet zone does encompass the EUT. There are some issues with regard to using or I won't say issues. There's two ways of looking at a open area test site. And Scott, if you could move to the next, please. One of the things that we're worried about with regard to the open area test site is that there are a minimum set of dimensions that are necessary in order to qualify the site. There's two ways of doing it. You could have a round circle, which is your site, or you could have an oval. And the oval is used when you have a turntable, which allows you to turn the product and not have to relocate the antennas. So in the absence of a turntable, we have a round OATS antenna that is used. Excuse me, round OATS requires antenna to be revolved around the EUT. Scott, if you'll show the next. So here's an example. With no turntable on the OATS site, we've got a ground plane, which is the boundary of the area. We're taking a measurement from 3 meters, 5 meters, or 10 meters away, which is the test antenna location that you see up on the top center of above the boundary of the EUT. And then the ground plane extends 1.5 times the measurement distance. So if you're using a 3 meter, you go 4.5 meters in length. However, you would have to locate the antenna all the way around the product in order to ensure that you're picking up all transmissions in all directions. And obviously that's time consuming. It's just not a good way to do things, obviously. So the alternative on the next slide, please. Oh, again, here's just a more of a enlarged view. Again, seeing the test antenna location, we're rotating at 360 degrees around the EUT because the EUT is not rotating. Next slide, please, Scott. If we have the turntable, then we can rotate the EUT. The ground plane then becomes an oval or an ellipse. the length is usually 2 times the distance D that you're measuring, in which you have half the distance, additional distance. In other words, if I have, let's say, a 3-meter chamber or a 3-meter measurement distance, then I will have to have a clearance of 1.5 meters behind the turntable and 1.5 meters behind the antenna, therefore giving me 2 times the distance D, and half of that distance each is between the test sample antenna and the boundary, and then the others are behind the antenna and the turntable. If you turn to the next one, Scott, this gives an indication of what I'm talking about. We have our test sample with D over 2 behind it. That's an extension of the ground plane in the oval. And then we have the measurement distance itself. And then again, we have that measurement distance over 2 behind the antenna. And that is our major axis, which is 2 times the distance of what your measuring distance is. So with a 10-meter 10-meter sight, we're actually looking at a 20-meter length of ground plane. And so once again, this is for an open area test site in which it has to be followed outdoors and not inside of a SAC or semi-anechoic chamber or a fully anechoic room. Next, please, Scott. We classify the open area test sites too by the amount of noise that is in the area. So Class A is the ideal situation in which all ambient emissions are 6 dB or more below the measurement levels that you have to go to. Class B, you have some ambient emissions that are within that 6 dB of the measurement. Class C, you have emissions that are above the measurement levels, but they're sporadic. They are spaced very far apart. They're aperiodic, which allows them to be sufficient space between when they transmit that you can still take a reliable measurement before it comes back up again. Class D is the ambient levels are above the measurement levels over a large portion of the frequency range, and basically it is unacceptable and unusable. And again, when we get into OATS and Wi-Fi's and other transmission sources, we find that a lot of noise could actually occur in that level of Class D. Although most of them, if they're in a quiet area, if you're out in the woods, if you're remote from an urban area, then you could probably still build an OATS at this time. But it is becoming more and more difficult. And also a lot of people don't want to have to trek out into the middle of nowhere and work outside with the rain and the snow and everything else that's going on. So having a semi-anechoic chamber, a fully anechoic chamber, makes it a lot more convenient and easily operational. Next, Scott, please. So I've talked about SACs and FARs. One's semi-anechoic, one's fully anechoic. That basically means that one is lined with, semi-anechoics are lined with ferrite, and at the same time they have absorber located in specular regions, which allow you to reduce reflection so that you're able to create the quiet zone that you're looking for. They all start with a shielded enclosure, which is basically a Faraday cage. The door, the honeycomb vents, electrical power filters, pipe penetrations, bulkhead panels allow ingress of certain things like power, like air, like compressed air, water, if you need it. But each of those, again, are specific or again, the door allows ingress of a person to go inside. So they're all there to allow for entrance into the chamber, but at the same time, it does not reduce or block or take down the shielding effectiveness of the chamber. Instead, it is maintained with the shielding effectiveness of 90 to 110 dB from 15 kilohertz to 40 gigahertz. This eliminates or drastically reduces all ambient emissions so that you can conduct your testing in a quiet area, a quiet zone, a RF quiet, a radio frequency quiet area. Next, please. SACs are, as I mentioned earlier, the shielded enclosure. They have ferrite lining on the walls and ceiling. CISPR 25 chambers are also very similar in that they are shielded enclosure. They have ferrite and absorber on the walls on the inside. With the case of the SAC, you could have a partial lining of absorber or a full lining of absorber. The ground plane exists on the ground, is inside the chamber. Is used for 30 megahertz to 1 gigahertz. When you do above that. When you get into 1 to 18 for SVSWR testing, then a ferrite tile and absorber patch is placed on the floor to absorb so that you're not getting any more reflection off the floor. However, from 30 megahertz to 1 gigahertz, being the longer wavelengths, they would like to have reflection as well to try and get as much measurement as they possibly can in those areas. And again, we look at 3, 5, and 10 meter measurement distances. Most 10 meter measurement distances are applicable to ISM applications and CISPR. Which one's ISM? CISPR 11, which covers which you can do 10 meter distances. However, you can also do a measurement at 3 or 5 meter, and then you can extrapolate to what that measurement would be at a 10 meter distance accordingly. So we see 10 meter chambers still being built, but we also see 3 and 5 becoming popular in that real estate internal to a building is just as valuable nowadays as it is external to the building. So next, Scott, please. So this gives you an indication of what a chamber looks like. Ferrite on the walls and ceiling. In this case, we're doing SVSWR testing. So we've got absorber on the floor, and the turntable is holding the EM test volume, or the EMI test volume is located above the turntable. And we're looking at a 3 meter measurement distance from the receive antenna, which can be raised and lowered to a height of 4 meters as required under CISPR 16. This is done for both SVSWR and for NSA, which means it's done from 30 megahertz all the way up to 18 gigahertz. Next, please, Scott. And then here's an overhead view in which, again, we're looking at the patch on the floor. And in some instances, some customers will put absorber, or it is required to put absorber on the turntable in order to meet SVSWR. Excuse me. Depending on the manufacturer of the absorber and the ferrite. But for the most part, we at least have to make sure that we have the area between the turntable and the antenna. Basically, we have that grid of absorber in order to absorb for SVSWR measurement testing. Next, Scott, please. This is a semi-anechoic chamber. You can see the ferrite tile on the walls, and then in front of that is the absorber cones. The ferrite usually provides the absorption necessary to reduce reflections within the chamber from the 30 megahertz to 1 gigahertz range, and then the absorber cones operate from the 1 gigahertz to the 18 gigahertz range. If you are only doing testing from 30 megahertz to 1 gigahertz, you could possibly get away with not having the absorber cones and just the ferrite. But if you're going from 1 to 18 or 30 megahertz to 18 gigahertz, you have to have the ferrite because absorber only is effective down to a frequency of about 750 megahertz. Anywhere below that, you have to have ferrite to absorb. So in the case of a SAC or even a fully anechoic room, you'll want both ferrite and absorber in order to run the full value from 30 megahertz to 18 gigahertz. Next, Scott, please. These cones are available in a variety of colors. Not all of them are attractive. However, they are used to provide the idea of identity for some companies where they like the colors because it is in their logo or it's in their application. But again, this shows an indication of a ferrite lined wall and ceiling with absorber in the specular regions around the turntable, which actually there's no turntable there, but that it basically shows that type of application. Next, please, Scott. So far is the same thing, except instead of a shielded enclosure with ferrite and absorber in specular regions only, you're pretty much lining the entire wall, ceiling, and floor with absorber. It simulates a free space environment. You're basically measuring only directly off of the product. You're not picking up on the reflection from the ground plane because it is also covered on the ground with absorber. What you're basically doing is creating a quiet environment that's allowing you to take a direct measurement off of the product. FARs can be used in place of a SAC, but again, there's a limitation with regard to the size of what you can measure in a FAR. The quiet zone is actually elevated above the ground floor rather than on the ground floor, which then allows it to give you, it has to be located at least 1.5 meters usually above the ground floor is your quiet zone. So you actually literally have to raise the product above the ground floor in order to be able to take your measurements. Next slide, Scott, please. Here's an example of where the product would be sitting on the Maturo mast, and it's above the area, and it raises the location of the quiet zone. So in this case, the quiet zone is located above the ground plane rather than on the ground plane. Impossible to be able to do testing with regard to floor-mounted units, for example. So this is not one that's popular unless it's small objects that are going to be placed in the quiet zone. But again, FARs have their uses, and you are able to cut down on the amount of ferrite, for example, and just use absorber cones, and they can be made to work in smaller environments. Another aspect with regard to FARs, which is critical, and I should have mentioned this earlier, is that you do not need to go to a height of 4 meters in order to take the measurement. Your measurement can be taken only directly from the height of the product itself. So if you have limitations, for example, in height, and you cannot place a full 3-meter chamber in your room because you don't have 21 feet clearance going to the ceiling, you can put in a FAR, but again, it's only going to be for small projects and small items that can be measured. So it's a limited application, but it does solve some issues for those people who have low clearance with regard to their rooms and still have small products to measure. Scott, next, please. So site standing voltage wave ratio is, and I'll refer to it from now on as SVSWR, it's a lot easier, is basically a measurement in order to qualify the quiet zone, which is usually the perimeter of the turntable. Very often, if you have a turntable, most customers would like to encompass that or know that if their product is on the turntable and encompassed by the turntable, then it is encompassed as well by their quiet zone. So very often, when you see the drawings or the illustrations that we'll be going over, you'll see that we're using the edge of the turntable. That's because that's also, in this case, we're assuming that that's also the edge of the quiet zone. What happens with SVSWR is that we have a variable height receive antenna, which is located at a specific measurement distance, usually 3, 5, or 10 meters away from a variable height transmit antenna. Depending on the size of the quiet zone, we may have to transmit at both 1 meter and 2 meters, for example, above the ground plane in order to qualify a 2-meter high quiet zone, for example. The variable height transmit antenna at the center of the OATS is at positions at left, right, and forward, and I'll show you those in a second. The broadband antenna method is most commonly used for site validation. We do both horizontal and vertical measurements and qualifications, and it's also for the H and E plane antenna radiation patterns. That's just basically saying that you should be able to use a horn antenna, for example, to do this testing, or even in some instances a log periodic with a high range that goes up to at least, in this case, I've seen them up to 6 dB or 6 gigahertz. But again, for the most part, we usually use horn antennas to do this. 2 copolarized antennas, both vertical and horizontal, and it operates off a 50 ohm system. Next, Scott, please. This is the test volume. This is an example of the test volume as illustrated in CISPR 16-1-4. It's cylindrical. Doesn't have it. It basically is, again, look at the bottom. You're basically sitting on the turntable, and that's very often what we do is we create a room. We ask the customer what size quiet zone they want, and they choose the size of the turntable that they're putting in there, and then we design the rooms accordingly to allow for sufficient free space around the quiet zone and at the same time specific absorption locations in order to qualify that there is no reflection, and we're able to establish the quiet zone following normalized site attenuation from 30 megahertz to 1 gigahertz and SVSWR from 1 gigahertz to 18 gigahertz. Next, please, Scott. Excuse me. So as you can see in this case, we've got locations on the turntable, or in this case, the quiet zone. But again, let's assume that the quiet zone is the turntable, in which we are locating the transmit antenna in the right location, the left location, the forward location, and in some instances, you may have to go to the center location as well. We'll go through a little flow chart that shows whether you need to do that or not. The antenna is moved at R1 to R6, F1 to F6, L1 to L6. So right, left, and forward and center, the antenna is moved. And the transmit antenna and the receive antenna remains stationary. At the same time, the receive antenna is always facing towards the center of the turntable and the quiet zone, but the transmit antenna, whether it's located on the right or the left, is then pointed at the receive antenna and not pointed forward, because the receive antenna is going to stay in that position when you're actually doing measurements of the product. You do not vary it to the left or right of the quiet zone. It simply encompasses the quiet zone. So when we do SVSWR testing, we make sure that the antenna stays at that value. When we're doing NSA, we actually point the antennas at each other for normalized site attenuation, but for SVSWR, we make sure that the antenna faces forward only on the receive, and the transmit antennas are pointed towards the receive antenna. Next, Scott, please. So basically, we take measurements at, let's take, for example, the front at F1 through F6, and this gives you an indication of what those measurement, what the distance is between the receive antenna and the transmit antenna, where F6 is the measurement distance, excuse me, and then we move it back a little, and F5 is 2 centimeters plus F6, F4 is 10 centimeters plus F6, F3 is 18 centimeters plus F6, 30 is F2 plus F6, and F1 is located 40 centimeters away from the measurement distance originally. We do not move the receive antenna. The receive antenna remains stationary. We only move the transmit antenna. Now, when we do NSA, we take measurements where we connect and take a direct measurement of the conducted power that's being sent out, and then we connect it to the two antennas, the transmit antenna and the receive antenna, break that line, connect those to the receiver. So instead of connecting from the signal generator directly to the signal to the receiver or spectrum analyzer and taking measurements across the frequency range at a set value, then we break it and connect the signal generator to the transmit antenna, and we connect the receiver to the receive antenna, and taking into account distance, taking into account gain of the antennas, taking into account loss of cables, we take a measurement and we measure. We then compare that measurement to what is existing and written into the CISPR 16 standard, which is the ideal number for an ideal site. And then through calculation, we determine whether each of those measurements are within plus or minus 4 dB, and that is what's acceptable. When we're doing SVSWR, we're not doing that. Basically, we're taking these measurements from position F1 to F6, for example, on the forward position, and then we're doing a ratio of the highest value measured and the lowest value measured. And that is our site standing voltage wave ratio that we have, that gives us an indication as to whether the product is in compliance or not. So we go from front positions F1 to F6. We go to right position from R1 to R6. Scott, next line, please, or next slide. Scott?
Hang on.
Okay, thanks.
There it goes.
Thank you. You can go ahead and jump ahead too. Same thing with L1 and C1. We're basically adding that. Yeah, you can go ahead and do it and jump ahead, but that's basically what you're doing. So in addition to the locations that we just went over, an additional SVSWR test plane at the top of the test volume may be required, depending on the height of the test volume. So I mentioned earlier that if you have to go up to a height of two meters, for example, in a quiet zone that's 2 meters high, then you we'll do the same testing at the second height at the front position only. But you'll do all the testing on the first height across left, right, and forward. Next, please. So this gives you an indication of the test volume. If you're going to 2 meters, then you have to take a second set. If you're going to 1 meter above the bottom of the volume, then you can take just a single set. But either way, you have to do, and your SVSWR is done at 2 meters and at 1 meter, and each of those data are compared not to each other. In other words, I don't compare the 2 meter to the 1 meter data. I compare all the 2 meter data to each other and take that standing ratio from there, and then I do the same thing from the 1 meter distance or 1 meter height. Next, please. Sure.
There it is.
So this gives you an indication as to what you have to do. You take your measurement on F1 on the forward position. If it passes, then you go to the left and the right position, and you do that testing. And then if that passes, if your test volume diameter is greater than 1.5 meters, then you also have to do the center position. And if that passes, then you ask, is the height of the quiet zone or the quiet zone basically greater than 0.5 meter? And if it is, then once again, you have to do a measurement at the front F1 at the second height value, which is 2H, and 2V, which is 2 horizontal and 2 vertical, which is basically the second measurement at the top. And if that passes, then your product passes and is within specification. Now, when we say pass, we're going to take these measurements and then we're going to use that data in the following formulas and in the following process. Scott, if you can move to the next, please. This basically just gives you an indication of how you designate F1H, 1H, for example, in which you are taking the front measurement. It is at a height of H1, and it is at the first horizontal position. Then F1, H1V is, again, front, height of H1, vertical measurement rather than horizontal. Okay, and that's at F6. Then you add 40 centimeters, 30 centimeters, 18 centimeters, 10 centimeters, 2 centimeters, and your reference position is the front page, is the front one initially. So you're basically measuring all of these values. And again, it's at those dots that you saw earlier, each one located a little bit further from the receive antenna. Next, Scott, please. And you do that on front, left, right, and if necessary, center. If it's greater than 1.5 meters, for example. And you do it twice if you're over 0.5 meter in height with regard to it. Now, this gives you the following procedure, and basically it's what I've just talked about. You take your measurements, you locate the receive antenna in a horizontal position at the test distance D, you measure from the source to the reference point of the receive antenna. You verify that the receive signal displayed is at least 20 dB above the ambient so that you're not losing the signal in the weeds. It's well above it. So you generate that value sufficiently high enough so that you're 20 dB above the ambient noise. And then you record your measured level, signal level. So again, we're not comparing this to ideal. We're just comparing it to each other. And we take all the measurements across the frequency range, then relocate the antenna back, take the measurements again, relocate the antenna back another 40 centimeters, do it again, 18, 16, all the values that you just saw. So you've got all this data. Then you change the polarization, you do it again in a vertical aspect. And then after doing F, you move to right, you do the left, and you do the center. Next, Scott, please. One of the things that we also do is we have to qualify what we're measuring. Because we're not moving the receive antenna to stay at that 3 meter distance, we're actually moving it a little bit further away. We're actually going to have to qualify the measurement that we're taking for the distance that it's being moved. Scott, can you go back one for a second?
Okay, well, right there.
Okay. That's called normalizing. If you look, it says under letter F, for all measurements, normalize the measured field strength of the voltage data to the distance of the reference position. So, and then if we can move forward again to the next slide. This is basically saying my measurement normalized is equal to the measurement I took plus 20 log of the ratio of the distance I actually measured over the distance reference, which would be 3 meters, for example, or 5 meters or 10 meters, and in dB. And then once you have that value, then you use that value to do your calculations. If you can move to the next slide, please. And that calculation is basically you take your voltage max and your voltage minimum, or your field measurement, Emax versus over Emin, and those are received signals, and that ratio should be then plugged into the what you see below, which is basically 20 log of Vmax over Vmin, or 20 logs of log of Emax over Emin, and that ratio should then be, if you go to the next slide, either less than 6 dB or less than 2 to 1 between the highest and the lowest at the front value, the highest and the lowest of the 6 measurements you took on the right, the highest and the lowest in ratio on the left, and the highest and lowest in ratio in the center for both the 1 meter measurement that you took and the 2 meter measurement that you took. If all your SVSWR ratios, or in this case, you can do it with dB and subtract it instead of taking the 20 log. If both of them, or either one, is within this specification of less than 2 to 1 or less than 6 dB, then your site is qualified for 1 to 18 gigahertz. Next slide, please. Any questions?
Open your microphones up if you have some questions at this time.
Yeah, I'll jump in first. So on these FARs, this is for EMC measurements only, obviously. This is not for antenna measurements.
That is correct.
Okay.
This is for site qualification of a SAC for 3 meter, 5 meter, or 10 meter measurement distance under CISPR 16 1-4.
Okay. One thing when on the frequencies from 1 to 18 gig, when you're doing the qualification, when you're raising and lowering the antenna from 1 to 4 meters, are you keeping the antenna bore sighted? Or is he just
actually, when you're doing this, you actually keep both the receive antenna and the transmit antenna at 1 meter.
okay?
And then you raise it to 2 meters, both the transmit and the receive antenna at 2 meters. They don't actually have to go all the way up to 4 meters.
Oh, okay.
I'm sorry, I didn't mention that earlier. So thank you. Good question.
I'm good.
Any other questions?
Yeah, hi. Yes.
Hi.
Yeah. So here, any antenna we can use, or any special type of antenna required for this?
No, for the most part, the antennas are usually horn antennas that are used. I haven't seen anything which requires specifics. You just have to have them. A double ridge horn usually is used very often to cover the entire frequency range, but they have to be available to be either rotated physically, or there is ways in which you can actually switch the input connection, but they have to be able to operate at both vertical and horizontal positioning. But most of the time, it's just a horn antenna from 1 to 18.
Are you looking for
Okay.
a fairly broad band horn with a wide beam width? Okay.
We are, absolutely.
Okay. This NSA not applicable below 1 gigahertz?
Yes. I have a
Okay.
presentation that I did for NSA. Scott may have a copy of it. You might be able to request that from him. If not, if you guys have my email address, you can email me, or I'm LFEUDI at Raymond EMC, and I'll send you a copy of that presentation as well.
Yeah, sure. Thank you.
On our website, emcsociety.org, right there on the front page, it says many of our meetings are recorded, and you can click on that link and you should be able to find Lou's past presentations there.
Awesome.
I have a question. I had typed this in the chat, but apparently nobody's responded. So will the slides, and not a meeting recording, be offered after the presentation? And if so, how do I request a copy?
So, Lou, if you want me, I can make these slides available to
No, I
all
don't have
the
a problem with that. You're welcome
registered.
to distribute it to anybody who needs it or
Okay,
wants it.
so whoever registered for this meeting, I will send the slides and a link to the video or video and audio. Okay.
Very good. Thank you.
More questions?
All right.
Yeah, I had a
Go ahead.
question. Um, the you said that this was from 1 to 18 gigahertz. I just didn't quite catch the part. What would you do for an open air test under a gigahertz? You said,
That's when you do the NSA testing, which
okay,
is the other slide presentation. It's the other measurement system that is described. It's the one I described earlier, in which you're
okay,
taking the conducted measurement first, and then you basically break the line and you connect it to a receive antenna and a transmitted antenna, and take your measurements again. And that's compared to a appendix, a table in Appendix J, I believe, of CISPR 16-1-4. Which
okay,
is your ideal numbers. And then if you're within plus or minus 4 dB of those numbers, then you get qualified with regard to 30 megahertz to 1 gigahertz. So it's a different procedure, different process, but similar in that you're qualifying the quiet zone for 30 megahertz to 18 gigahertz.
okay. What about like under AM band or to like 30 megahertz? Is there anything for that, the qualification for that?
There is not been so far, but at the same time, CISPR 16-1-4 is in the process right now of preparing to put out requirements for doing measurements in the magnetic field range, basically for loop antennas. And I will probably be able to do that as a presentation for you guys next year.
That'd be very cool.
Yeah.
And sorry, my last question is, you mentioned that a forest chamber can do RE and radiated emissions in a smaller space than a SAC, the semi-anechoic.
A shorter space, yes.
Shorter. Okay.
Yes.
Because I have like a 10-foot by 10-foot chamber that's for conducted emissions, and I thought it was too small to do radiated emissions.
It's difficult to do radiated emissions because most of the time NSA requires that you raise, and just in general, the requirements are that you raise and lower your antenna to a height of 4 meters. And in the case of VSWR, someone mentioned earlier, you have a bore sight antenna, which actually leans forward so that the antenna, as it goes up, is also pointing still at the product. And then coming back down, it's still pointing at the product. That's
Okay.
what's normally required, and that's why a semi-anechoic chamber is used to do that. But the FAR allows you to use it where you don't have to raise it to a height of 4 meters, but at the same time, and so therefore you don't have to have that 4 meter clearance to do it. But at the same time, it's very small as to what you can measure, and the quiet zone is a lot smaller and it's elevated, so you can't take large products, nor can you do products that are floor standing. So it has limitations as to what you can measure. But if your product meets the specification, you can look at doing a FAR if you have small height requirement in your building to put a chamber in.
Okay.
Will that allow you to go down to 30 meg, or do you
Yeah.
have to stay in that? Okay.
Yeah, no, you can actually operate on a FAR the same way that you would in a SAC or an open area test site, and take all measurements from 30 megahertz all the way up to 18 gig.
Okay. What's the size limitation on the DUT or the quiet zone?
That depends on the size of the quiet zone, I believe. I'd have to go back and check. I believe that there is a 1 meter maximum.
Even that sounds big, yeah.
Yeah, it is rather big. For it varies. It's in my other presentation as well. Like one of the last slides, it varies from the 3 to 5 to 10 meter, and the size of the quiet zone reduces. So I think it goes from 1.5 meters at the 10 meter distance to half a meter at the 3 meter distance, but I'd have to go back and double check it.
Okay. Thanks.
Any other questions?
More questions?
If that's the
Okay.
case, then thank you everyone for the opportunity to be
Thank
able
you, Lou.
to
Thank you
address
so
you.
much for presenting. Very nice. So, as we mentioned a bit earlier, we are going to make this recording and the slide deck available to everybody. We even got a clap floating up the screen, a couple of them here, so that's good, Lou.
Oh, well, thank you. I wish everyone a very happy new year and a good year this year and a prosperous year this year. So thank you, everyone.
Thanks, Lou.
Sam, thank you.
So at this time, if there's no more questions, we're going to do the raffle. So I misspoke earlier, but I guess I have to stick to it now. Usually we do 25, 50, 75, but I said 100. So we're going to do 25, 50, and 100 this time, which is okay. So I use a random number generator from random.org, printed out before the meeting, and then we run this against the event roster. And that's how we do this. You must be present to win. So we're going to start with the $25. And I think I'm going to stop the recording now.